Mike Slater. This is work done as a PhD candidate at MIT with my advisor, Devarit Shah. By the end of this talk, you will have heard about a key forecasting and estimation task in finance. How do you predict or track the financials of companies? For example, what will Chipotle's sales be next quarter? To give some context to the problem, tracking company financials is of great interest in a number of industries. So the problem is company financials are hard to observe directly. So analysts look to proxy signals. Proxy signals are things like credit card transactions. Google shows you ads online. Do those ads cause you to end up walking into a physical store and spend money? To assess the impact of ads, Google buys credit card data to see what happens in retail stores. Tracking revenue of companies is useful for asset pricing. So hedge funds spend hundreds of millions of dollars a year on data sets in the hope of being able to track public companies better. I mentioned transactions, but the general category of proxy signals for company financials is called alternative data. These types of data are alternative to direct disclosures from companies. Direct disclosures would be things like SEC filings or press releases. Instead, alternative data is side channel information about companies. Alternative, or alt data, consists of data sets that are a little unusual and try to measure company performance in a roundabout way. There are lots of types of alt data: credit card transactions, satellite images to monitor the parking lots of retailers, smartphone location data. This is the plot of the number of vendors selling alt data by year, which is one of the hottest types of information in finance right now. However, quantitative methods are very much lacking for utilizing this type of data. We focus on one type of alternative data, transactions data, like credit card, debit card transactions, which act as a potential proxy for company financials. There are lots of places to buy this data. We obtain transactions data from a large hedge fund. There are lots of use cases for transactions data, trying to monitor and estimate growth at different companies, or assess a company's credit risk, or how online ads translate into in-store spending. In many of these cases, data and insights are revealed in an anecdotal manner. A lot less work has been done quantitatively. So we're focusing today on utilizing alt data sets in a quantitative fashion. To start, I will briefly describe the key elements of public company financials. So in this work, we focus mainly on public companies. What's special about public companies? They have quarterly reports. So every 90 days, public companies are required to disclose key financial information. For example, we see Chipotle here in the first quarter of 2017, disclosing its total revenue over the quarter. The other thing you'll notice here is that every 90 days, we get only one data point. So you can imagine that if you're a hedge fund trying to price Chipotle stock, or if you're Domino's Pizza and a competitor of Chipotle, you might be interested in understanding what's happening more frequently. And hedge funds and competitors are also interested in forecasting this one number in addition to tracking financials more frequently. So as a running example today, we're trying to estimate what happens to Chipotle revenue with more frequency. And so we're trying to, one, predict the final quarterly number, and two, come up with some way of estimating what's happening earlier in the quarter. Summarizing the vision, we want to track companies with higher frequency and forecast their financials. And each of these tasks is of interest to a number of different industries. So to accomplish this, there are two parts: data and a model. So first, we need to identify data sets that contain higher frequency information about companies. We expect this type of data to be noisy and imperfect. Next, we need a model to make use of that data. So we're going to, as mentioned, make use of alternative data, in particular transactions. And for modeling, we will use the classic linear dynamical systems model, but with a particular state space constraint. Back to our running example, this is what our data landscape looks like. We have credit card data in magenta. We get this with some frequency, daily, weekly. Here I drew biweekly. The credit card data records some unknown fraction of total Chipotle sales. The black circles are the unknown ground truth that is never disclosed. And this is what we want to estimate. And the green star is the disclosed revenue from the quarterly report at the end of the 90 days. So this is what our data looks like. Now, to make use of the alt credit card data, we need a model. So what types of models could we use? We can't use any type of model that requires fitting lots of parameters. There are labels 4 times a year. The alt data sets go back at most a few years. And the high frequency data comes in something like once a week. So we can't use deep nets or recurrent nets, for example. One key element that we'd like is to quantify the uncertainty in our estimates. So we want models that produce actual probabilities. In addition, we'd like a model that has a corresponding data generating process. We'd like to be able to generate fake synthetic data to validate our theorems, algorithms, and code. Since there's so little real-world data, we need to test and validate our algorithms first on synthetic data, just from a practical standpoint. Natural starting point would be to see if just a simple linear model is tractable. So for simplicity, let's assume we're only talking about real numbers and scalars. but everything applies in the case of vector valued company financials, which is what's in the paper. So first, actual revenue. We're going to model true company revenue as evolving according to some linear process. So if T is the day, then the revenue tomorrow is a linear function of today's revenue plus noise. This is definitely not how actual company revenue evolves, but it's a first pass linear approximation. So next, for alternative data, we model the alt data or transactions of these observations also as a linear process. The Y's are like credit card data, which is some unknown fraction of, say, total revenue, and the observation process is noisy as well. Last, quarterly reports. So if T is 90 and gamma sub 90 is 1, that would be a quarterly report. That is, if gamma sub 90 is 1, we observe the sum of the total revenue over the quarter. I'll talk in terms of quarterly reports for most of this talk, but there's nothing special mathematically about 90. Later, we'll discuss modeling gamma T according to a Bernoulli process. So this is a rough first pass at a linear model one could use, which is a reasonable starting point for modeling a time series with very few parameters. This is a graphical model for the problem. There's a bit of notation abuse. We're showing the S's twice, but that's just to indicate it's observed. So the key questions are, one, how do we determine the model parameters? And two, how do we use the model to infer the latent revenue numbers? Then forecasting S sub 90, for example, would be straightforward once we've solved these first two problems. So we make three contributions. We have, first, a cohesive framework for incorporating both the high-frequency alternative data, or side channel data, along with intermittent aggregates, like quarterly observations. Next, we solved the two problems that we needed to utilize the model. First, system identification. It's surprising that we can actually solve the problem of learning the model parameters. It's normally theoretically unresolvable. It turns out that the inclusion of quarterly observations allows us to devise consistent estimators, and some of the estimators are unbiased. And we also provide a finite sample analysis of the error. And then inference, given a model and model parameters identified, we show how to estimate the hidden revenue numbers. And we do this with bounded estimation error independent of the model parameters, and monotonically decreasing errors, we get more and more quarterly reports. Last, applications. We use our end-to-end algorithms to outperform the Wall Street consensus estimate in predicting quarterly financials. So to give a little background on system identification before stating the results, for a minute, consider our setup without the quarterly reports. So this becomes a classic problem in linear systems. There's no single optimal solution unless you place constraints on the parameters. I want to highlight the key issue in determining the parameters is that we do not observe the x's. If you knew the xt, it would be easy to determine all the parameters. For example, if you knew the x's and we have y's, determining c is just regression, but we don't know the xt. So this plot highlights the issue with system ID or finding the parameters. For this plot, we start with a data set generated from fixed parameters, and the true value of a, the autoregressive parameter, is a half. That's the green line. But let's assume we don't know a. So on the horizontal axis, we're trying different guesses for a, and then we compute the likelihood as a function of that guess. The actual true a is the vertical green line. The maximum likelihood solution is the dotted red line. These don't coincide. So the MLE is biased, and in addition, it's non-convex. In general, there may be more than one combination of parameters that give rise to the maximum likelihood. So this is just visually showing that finding the true parameters is unresolvable in general. So what can be done? One option, heuristics, like expectation maximization and the subspace method. These are approximate techniques that start by approximating the latent variables and then estimating the system parameters. However, none of these heuristics provide theoretical guarantees for finite samples. And often the heuristics that exist result in poor performance. You could try brute force, like multiple model adaptive estimation, try lots of parameters, then do residual analysis, hypothesis testing. Change the problem is the third category. Like you could assume that there's no process noise, and then that can be solved with a gradient descent-like approach. If you only want to predict the y's, you can construct a model that mimics LDS for predicting the y's, but we actually care about the x's. You could place constraints on the parameters. And then there's recent work on low-dimensional approximations to the system. So we live in this third category of problem variations, but we do so by incorporating additional information, in our case, quarterly reports. So it turns out the added quarterly constraint number is significant. In fact, if we observe ST with any non-zero frequency, then we can provide consistent estimators for all the parameters, and our estimators are unbiased for half the parameters. So my intention is not to walk through this in detail, but rather I want to show the form of these estimators on the right. So let's just look at the estimator C hat. The form of this estimator looks like OLS, ordinary least squares. The question is, how do we get to OLS from the system equations, which are in gray at the bottom? I'll briefly go through derivation for this estimate. So first, just to define some terms. The tilde SI are normalized quarterly reports. The numerator is like quarterly revenue. The denominator is like the square root of 90, or like the square root per day. So this is like something like the average revenue per root day. The Y's are aggregates of alternative data. So this is the tilde YI are something like the average observed credit card spend per root day. Equation 1 follows from the system equations. To get here, we just multiplied the quarterly aggregates by the unknown observation matrix. See, this is like an observation equation of aggregates. So equation 1, the right-hand side we know, it's the aggregate observations. The left-hand side we have SI, which we know, that's a quarterly report. There's additive Gaussian noise, which is the sum of ID Gaussian noise, and C is what we're looking for. So this looks like multiple multivariate linear regression, since the target or the right-hand side is a matrix in general. With everything normalized, we get equations 3 and 4, which just says that the noise has the covariance matrix that we're interested in. So line 4 looks like regression with additive ID Gaussian noise. So we can just use the standard theory of linear regression. However, we have to treat this carefully because the features are stochastic, but we can now use standard results on regression. So in particular, these are the two key theorems for the parameters in the observation equation. This says our estimators for C and R are unbiased and consistent, and the error in our approximation for C scales like log K by K, where K is the number of quarterly reports. The derivation for A and Q, which are in the latent process, is more involved, and so I'm not including that here. But this table summarizes the properties of our estimators. They're all consistent, half are unbiased, and we have finite sample analysis for C. A note on sparsity. So our estimators can be computed even if almost all of the data is missing, as long as we're given certain aggregates. So we just need 1, quarterly reports, 2, aggregates of observations, and 3, individual observations only in a small neighborhood around quarterly reports. Next on inference, the first task was estimate the system parameters. Now we consider, suppose we know or estimate the system parameters, how do we infer the latent X's or the latent daily revenue? So I'm going to skip over this because of time constraints, but we end up using a modified version of the Kalman filter equations. Now, Bruno Sinopoli and others have done related work here, but they assume that at each time step we get either a complete observation or nothing at all, as opposed to partial observations. So we prove, as a couple examples, 1, that our inference equations are optimal in terms of mean squared error, and 2, we get end-to-end convergence, where if you perform our system ID procedure followed by inference, that converges to the optimal estimator. So now, application. So we look at testing our forecasting method on real data. So our goal is to predict the quarterly sales numbers at public companies. Our data consists of credit card data that we obtain from a large hedge fund. The data covers 34 public companies with 7 to 10 quarters of data per company, which means less than 3 years of data per company. Most of our data looks like weekly or biweekly aggregates of transactions. So here we're showing weekly transaction aggregates at a fast food retailer. These numbers are made up because I can't disclose the data. We have 12 data points per quarter or fewer, and we have at most 10 quarters of data per company. So that's a maximum of 120 unlabeled data points and a maximum of 10 quarterly labels. And in terms of how much sales we actually see in the credit card data, we often observe less than 2% of the actual, what turns out to be the actual total revenue per quarter. So then for testing, we use leave one out cross-validation, where we train on, for example, 7 quarters of data and test on the 8th quarter. So these are actual sample results for one company over 9 quarters that ended in 2019. So the benchmark that we're comparing against is an industry standard benchmark that makes use of full market history, where human experts help tune this benchmark. In general, it's pretty good. It's relatively low % error, a hard benchmark to beat. And it indicates how hard the forecasting task is. On some quarters, the benchmark has 1.5% error. For this particular company, we outperformed the benchmark on 5 out of 9 quarters and have lower overall % error. And then across 34 public companies and a total of 306 quarters, we beat the benchmark on every metric. So we have lower RMSE, lower absolute error, and on 57.2% of quarters, we are closer to the target than the benchmark. And that's statistically significant. So just a note on the significance of outperforming the benchmark. So this is an industry, finance is an industry of very weak signals. where companies try to monetize slight edges. So of course, there is a lot more to trading than just a forecasting edge. And the worse the edge, the closer to 50%, the more you would need to trade. And that may not actually be possible in some cases. And trading is beyond the scope of this work. But our work could be, for example, an input to a trading strategy. But the point is, any forecasting edge against this benchmark is significant. So summarizing the contributions, we developed quantitative methods for utilizing alternative data. We start with a data set of consumer transactions and focus on forecasting and tracking company financials, in particular aggregates like quarterly revenue. We outperformed an industry standard benchmark with our forecasts, being the Wall Street consensus estimates, and we look forward to your questions.